Good day, and welcome to the third presentation on ventilation equipment. In previous presentations, we've discussed the application of ventilation equipment and various aspects of cooling and providing fresh air to industrial and commercial buildings. After those presentations, which by the way can be found on the Airmaster website, it occurred to me that we did not discuss some of the basic aspects of selecting a ventilation product. You'll have to excuse me for this oversize because after nearly 40 years in the fan business, much of this information is just second nature to me, and I forget that others don't necessarily have this information. So here it is. As before, we're recording this presentation for those of you who are unable to attend. And, well, we did our best to make the information accurate, but occasionally we screw up. So if we do, would be wise to check other sources. I'm constantly amazed that engineers who should know better often ask for a fan that provides, for example, 86,411.6 CFM. Sometimes I just ignore this as I don't want to insult them, but if I know them at all, I ask them how they plan to measure this. The simple fact is that airflow just cannot be measured that closely. In a lab, you might be able to measure within 1 or 2% of a true value, but in the real world, in a plant, and with large amounts of patients, you would be lucky to get within 5% and more likely within 10. And the fact is, by the time you were even partway through the measurement, the conditions would change. Okay, I admit it. Like most everyone, I can be a little lazy from time to time. So this is a slide from a previous presentation. But I'm showing it here again because it does bear on the issue at hand, which is measuring actual airflow. Again, the actual operating point of a fan is always the intersection of the fan curve and the system curve, and it's not necessarily where you want it to be. And also, keep in mind that a system curve is made up of all the resistance to air movement, in this case, from outside of the building, through the building, and back outside again. This particular example shows what happens to this resistance when a large door is closed. But let's consider instead what happens with a slight breeze blowing outside. If the fan in this example was being used as an exhaust fan, just a breeze of 12 miles an hour against the wall in which it was mounted would be enough to raise the static pressure against which the fan is operating by 0.08 inches, which doesn't sound like a lot. Now, look at the curve starting at the green arrow, which is our design point, which is 0.125 inches of pressure. However, when the wind is blowing at 12 miles an hour, there's going to be an additional resistance of 0.08 inches, or a total of 0.2 of an inch. So we follow the fan curve starting at the green arrow, or the point with the original system curve, and the fan curve, and follow it to the point where the fan curve reaches around 0.2 of an inch. And the horizontal gray lines here are each 1/10 of an inch. So instead of the 11,000 CFM we're expecting, now at 0.2 of an inch, it's only going to be 10,000 CFM. So the wind has reduced the flow by almost 10%. So it just goes to show it really does depend on which way the wind is blowing. Moral: if flow is critical in your application, provide plenty of margin for upset conditions. But more important, this shows another aspect of having a difficult time in determining fan flow. In the context of a panel fan, velocity is the speed at which air moves through the fan and into or out of your building. So, for a given flow, the size determines the velocity. Velocity can be measured in all sorts of units, like miles per hour, for example. But for panel fans and this presentation, it will be in feet per minute. And in the third line, we show the formula for how this is calculated. Basically, you take the flow and divide it by the area of the size of the fan. With many things, higher velocity is better, but this is not necessarily true for panel fans. And we're going to show a couple of reasons why this is the case. But in general, all a higher velocity is going to achieve is turbulence and draft, which are not desirable for an air supply unit. And even for an exhaust unit, there's at least one good reason to avoid it as well. So select a fan with the lowest reasonable velocity. So what's reasonable? Of course, reasonable means different things to different people, but here's a little bit of guidance. 500 feet per minute is probably too low. 1,000 feet, well, it's okay. But the sweet spot is between 1,500 feet and 3,000 feet a minute. 3,500 to 4,000? Yeah, sometimes that's where you might want to choose, and we'll show some reasons. When you start to talk about velocities of 4,500 feet and above, you better have a good reason to want to do that. So here's a primary reason to avoid high fan velocities. It costs money. And this applies equally to supply or exhaust units. There are lots of numbers in the table. The quick explanation is that velocity can also be converted to a pressure, and the pressure then can be used to calculate a horsepower and power consumption. But the important numbers are the velocities at the left and the cost per hour per 1,000 CFM. The cost of per hour jumps up quite quickly because it's a square function. At right is an example for a 20,000 CFM at various velocities. So it's 20 times the cost per hour. And for this fan and 12 cents per kilowatt hour electrical cost, the difference between a fan at 4,500 feet per minute and one at 3,000 feet per minute is 33 cents per hour. For a single 8-hour shift, that means a difference of $660 a year, and that's every year into the future. So a small fan that seems like a bargain can actually be considerably more expensive when future operating costs are considered. Falling rain travels between 1,300 and 2,200 feet per minute in still air. If, however, the air in which the rain is passing is being pulled into a fan, then the rain is going to be dragged into the fan as well, which is, needless to say, not a good thing. This is a consideration for supply units. It is actually the opposite for exhaust fans, since the higher the velocity, it will help to keep the rain out of the unit, particularly in the case of wind-driven rain. Then the higher the velocity, the more resistance it's going to be to water penetration. I know, everything's a compromise. If rain is a big issue where you're located and you're selecting an exhaust fan, that you're going to want to run under rainy conditions, then you might want to consider a higher velocity in your selection. Of course, we've considered the issue of rain, and a weather hood will provide significantly additional protection. And, surprisingly, there's nothing to prevent these units being used on an exhaust fan, although it is very rarely done. Hot air rises, which is why there are such things as hot air balloons. But it rises even without the balloon around it, and it will stratify in your building with the hottest air near the ceiling. There are a number of good reasons that you might want to operate a supply fan year-round. But the challenge is that you don't want to blow cold air on anyone. A high-mounted fan with a somewhat higher velocity is a good solution, since the velocity is going to cause mixing with the warmer air before it descends to floor level. Is it a perfect solution? No. There are times when the outside air is so cold and the air in the building just isn't hot enough to make it comfortable, but it will work well most of the time. I have a huge amount of respect for acoustical engineers. Airflow is hard enough, but sound is way beyond airflow. And often, the people that really know about sound have a PhD behind their name. One reason for my respect and the cause of considerable heartburn on my part is once in a while I get a call from someone and that person says, "I've measured the sound that your fan makes." Right away, I know I'm in trouble because they didn't really measure the sound of the fan. They measured all the sound in the space that contains the fan. And if there's anything else going on in that acoustically in that space, then it adds to the sound of the fan. They're also measuring not only the sound of the fan itself, but the reflection and refraction of the sound in the space. So suffice it to say, you can't easily measure sound except in very special circumstances and in very special ways. Having said the preceding, it's rather surprising that we can in fact make some statements about fans with respect to sound. Keep in mind that they are statements about relative sounds. They are not statements about the absolute or the measurable sound of any installation. A huge source of confusion is the difference between sound power and sound pressure. Unfortunately, they both use the same units, which are decibels. By the way, that is 1/10 of a bell, as in Alexander Graham. Sound pressure is what you actually measure, and dB is a logarithmic scale that allows for a huge range of actual numbers. Sound power is a property of a machine in that it is the power the machine creates as sound. At a given size, speed, point of operation, this is a known quantity. However, converting from power to pressure is unfortunately a very difficult task. So what follows is comparisons of sound powers, which provides some basic guidance, but it's not really usable in establishing actual installed sound levels. Since, as noted, sound is logarithmic, then it's not surprising that in the formula for sound, logarithms of base 10 are used. This formula allows a comparison based on size and speed. Here's an illustration of what happens to a fan when you increase just the speed. We're using the HA24CA as the basis, so it's our zero, although clearly it actually makes sound. What we can say is that the sound power will increase by 10 decibels For an example, when the speed goes from 746 RPM to 1180 RPM of the HA24JA, it should be noted that 3 decibels is a doubling of the sound power. But it also should be noted that we humans can really not distinguish between a difference in sound power of 1 or 2 decibels. Perhaps of more interest is a comparison of different size fans which are providing similar flows. In this case, we're using a high-speed 24-inch as the basis of comparison. If you remember the formula, you would note that the change for size is 70 times the logarithm of the ratio of sizes. Wouldn't this increase the sound as we go up in size? Yes, absolutely. But what happens is that the reduction in sound due to speed in each example is actually greater than the increase due to size. Just the change from a 24-inch to a 30-inch is minus 6 decibels, which is a quarter of the sound power. Remember that 3 decibels is twice the sound, so negative 3 decibels is half the sound, or the inverse. So in this case, 6 decibels is half of a half, or 1/4 of the sound power. Just in passing, it should be noted that humans are less sensitive to low frequency. This is not accounted for in the comparison, but as the choice of unit shifts to larger fan, this too would reduce the perceived sound. Like all energy, sound expands outward from the source in a spherical pattern. Although, for a panel fan, we only have to deal with 1/2 of the sound since the other hemisphere is on the other side of the wall. The mathematics of this means that the sound level decreases with the inverse square of the distance. So, twice the distance means 1/4 of the sound, and 4 times the distance means 1/16 of the sound. So, sound dissipates fairly rapidly with distance unless reflected or refracted. But when you have 2 sound sources at some distance from each other, they can actually be additive. Here's a diagram of this type of situation where we have 2 identical panel fans. You will note that the little area where the circles overlap, if one walks perpendicular to the airflow in front of these 2 fans, you would note all of a sudden the sound increases as you traverse this region where the sound is overlapping. In practice, this means that using larger fans spaced further apart will have less of this phenomena because, remember, the sound is decreasing rapidly with distance. So the overlap will still be there, it just will not be as noticeable, usually. You'll notice that I finished the previous slide with the word usually. Here's a potential issue that applies to all situations where identical fans are employed. The problem is, even though they are identical fans, they don't operate identically. Small differences in the motor or propeller create a small difference in the speed. For most practical things, they will be identical. For instance, the flow probably would not be measurably different. But when it comes to sound, unfortunately, this difference can be noticeable in a very large way. In those areas where the sound is additive, what happens is the speed of the units match periodically. And what is happening is shown in the diagram. The diagram shows the height of the wave, which is amplitude or loudness. And the x-axis is time. So as the speed starts to match, the sound becomes larger. Rather interestingly, The sound wave can also cancel one another. So the areas with little or no sound are where this is happening. This phenomena is known as beat frequency or just beat, and it is typified by the sound level rising and falling. While this situation can be severe, normally it's not a huge difference in the sound level. The problem is that we humans are designed to notice small changes in sound. That's how we knew that the predators were creeping through the grass to make us into lunch. So the issue is, because of our sensitivity, beat frequencies can be very annoying. So this is another reason to use larger fans spread further apart, since this will reduce the possibility of this annoying situation. It won't eliminate it, but it will reduce it to the point where it is not noticeable. I could have made this presentation much shorter by just saying the advice is to always tell the customer to buy the largest fans. The problem, of course, is when you provide this recommendation, the customer just thinks, of course, that's what earns you the most money. But based on the engineering information that I've presented, you will now know that there are good reasons for this rule of thumb. Remember, this isn't always the case. Certainly, there are cases where physical limitations prohibit large fans, and there are also sometimes other reasons, such as wanting to have mixing inside the building, or in the case of an exhaust fan, to keep out driving rain. But most of the time, bigger is better. Thanks for your attention. Our hope is that we will have provided you with some information, and you will now have a better sense of how to choose a panel fan. Airmaster recognizes that there are all sorts of specifications and exceptions when designing a ventilation, and we're here to help. Shown on this slide is the contact information for Forrest Owen, our Ventilation National Sales Manager. So if you have questions, get in contact. Thanks again.